For many of us, higher math evokes a visceral sense of dread. Standing before a chalkboard covered in dense Greek letters and unfamiliar symbols feels like staring at an unscalable wall. This intimidation has a real-world cost. Every year, countless people walk away from promising careers in science, medicine, and technology because they don't want to cross paths with this specific subject. They limit their own potential to avoid a headache. This anxiety is usually fueled by one massive misconception: the idea that calculus is a purely abstract nightmare reserved for specialized laboratories and rocket scientists. Calculus was invented specifically to capture the mechanics of our physical reality. It provides a formal language for motion and growth that static arithmetic simply can't describe. There is no magic at work here. The underlying engine of calculus runs entirely on the basic arithmetic, algebra, and geometry you already use. The difference is that calculus takes those rigid, static formulas and applies them to moving targets. It is the mathematics of continuous change. If you live in a universe where things move, accelerate, or fluctuate, you are already moving through a world governed by these principles. We can strip away the mystery by looking at the subject's three core pillars: limits, derivatives, and integrals. Once we see how they function, it becomes clear that we've been using them intuitively our whole lives. Let's start with the first pillar, limits. Mathematically, a limit calculates what happens to a value as you get closer and closer to a specific point. You experience this concept every time you try to parallel park a car. As you reverse, your brain processes a shrinking gap. You make tiny adjustments to the wheel and the brake to get as close to the car behind you as possible without actually making contact. This is a physical version of a numerical limit. You are closing a distance towards zero, using feedback to approach a boundary without crossing it. The concept of a limit formalizes this natural ability to navigate boundaries. It translates our physical intuition about proximity into a precise mathematical tool. That brings us to the second pillar, derivatives. In a classroom, this is defined as the exact rate of change at one specific frozen instant in time. Think about driving on a highway. Your speed isn't a flat line. It fluctuates as you hit traffic, climb hills, or accelerate to pass someone. If we plot that journey on a graph, the line is a constant curve of highs and lows. But when you glance at your speedometer, you are looking at one frozen millisecond of that journey. Your speedometer acts as a derivative machine. It calculates your exact rate of change, represented by this tangent line, at that one specific point on the curve. A derivative is the mathematical way of answering a question we ask every day. How fast is this changing right now? Finally, we have the third pillar, integrals. This is the process of accumulation over time. You see an integral in action whenever you check the step tracker on your phone or watch the odometer on your car roll over. Your movement throughout the day is chaotic: short walks, long periods of sitting, and occasional sprints. The tracker captures every one of those varying moments of movement and adds them all together. Integration is the mathematical version of that tracker. It gathers microscopic, varying changes and combines them into one sum total. An integral is the tool we use to measure the final result of a day's worth of constant, fluctuating changes. You've been performing intuitive calculus your entire life without ever needing to pick up a piece of chalk. Limits, derivatives, and integrals are just formal names for the ways our brains process destinations, speed, and total growth. The logic we use to park a car or track a run scales directly into our complex engineering. By applying these three pillars, we can calculate the wind load on a suspension bridge or the fuel required to launch a satellite. When we demystify the vocabulary, we remove the hurdle that blocks people from entering STEM fields. We stop seeing the math as an obstacle and start seeing it as a tool. Calculus is a practical language for a dynamic world. Once we recognize these pillars in our own lives, the subject becomes a way to better understand the world we already live in.